thank very much the organizers, Lorenzo in particular. Of course, it's a great joy and an honor to talk on the birthday of Jacob. So, yeah, so it's very difficult to talk about the whole mathematical work of Jacob. So I will try to focus on a topic that is particularly important for me because it was related to my thesis. No, I was a student of Jacob, but also I think has an important role in the mathematical work of Jacob, as Enrique stressed. So indeed, I thought it would be better to give my talk before Enrique, because Enrique went much deeper. I will, of course, mention this last great theorem by Jacob and Yarkos at the end, but I will start telling a little bit of the history of the subject and some older results, and so. But like Star Wars, they tell the beginning of the story after the middle, so I think it's okay. And then just you may remember this great Enrique's talk after the end of mine. So let's start with. Of course, the title is Jacob and homoclinic bifurcations. I'll talk on the several works of Jacob related to homoclinic bifurcations and works and conjectures, which were very central to the development of the field in the last decades. So homoclinic bifurcations are perhaps the most important mechanism that creates complicated dynamical systems from simple ones. And so we'll discuss some results and conjectures that support this statement. We cannot, so as Marcelo did yesterday in the Brazilian Academy of Science, we also quote Poincaré. So this is in this famous work of Poincaré on celestial mechanics, on this restricted three-body problem. And he realizes that the existence of homoclinic intersections, transversal homoclinic intersections, creates very complicated dynamical phenomena in that. So this is very classical. I'll tell a story that Jacob told me recently on how he became aware of of this story of Poincaré. So he told me that he was visiting Stockholm, so invited by Lennart Carlsson, and he saw physically these two versions of the same work by Henri Poincaré on celestial mechanics, and so this is Mittag-Leff Institute, and indeed, after that he became aware of this story of this prize that Poincaré won in the end of 19th century. Was a prize related to Acta Mathematica. The idea is to promote Acta Mathematica, to publish the papers winning the prize in one of the first editions of Acta Mathematica, and was a prize given by the King of Sweden. And so Poincaré did a famous mistake, but it led to very interesting mathematicians exactly related to homoclinic intersections. So he thought that a homoclinic intersection should generate a coincidence of stable and unstable manifolds. And then we realized that the typical situation is that the intersection is transversal, which implies a lot of dynamical complications. And as we know now, it implies the existence of horseshoes, etc. But Poincaré already, at that time, realized the great dynamical complexity generated by homoclinic intersections. And so there is a very beautiful paper by Jean-Christophe telling this story in Gazette des Mathématiciens, so that I recommend. But so let's talk on homoclinic bifurcation. Let's describe the simplest problem in homoclinic bifurcations, which is related to the study of homoclinic explosions in dimension 2. So you have a family of diffeomorphisms. In the simplest case, you suppose that they are uniformly hyperbolic for negative values of the parameter. You create a first homoclinic tangency at the first value of the parameter, at m equal to 0. And then you unfold this homoclinic tangency, and you want to understand what happens for most small positive values of the parameter. And so this is a picture. So here, before the bifurcation, you may have a uniformly hyperbolic dynamics, perhaps with a horseshoe as depicted here. This is a horseshoe, a uniformly hyperbolic set. You create a homoclinic tangency, which unfolds for positive values of m. So this is a picture for a positive value of the parameter. And you create a lot of new homoclinic intersections for many parameters after the bifurcation. And you want to understand the dynamics as Enrique described. You can understand in many different ways. So even for non-hyperbolic systems, you can have non-trivial results, as described. But this is somehow the end of the history. So I will tell the beginning of the history, so the most classical results on this. So homoclinic bifurcations are one of the most natural and most important ways of bifurcating from hyperbolicity. So have a structurally stable diffeomorphism, uniformly hyperbolic. One of the main ways of going to a non-hyperbolic system in most profound ways is through homoclinic bifurcation. There are many local bifurcations, like bifurcations that change the status of some periodic orbits, like saddle node, etc. But homoclinic bifurcations are more global in some sense, and indeed they create a lot of complicated dynamics. For instance, Sheldon-Newhouse showed that after any homoclinic bifurcations, you have some, perhaps small open sets of parameters corresponding to persistent homoclinic tangencies. And under some dissipativity hypotheses, this led to examples of open sets where residually you have infinitely many coexisting sinks, which is a very complicated dynamical behavior. And both, well, Newhouse and then Jacob and Floristakens showed that fractal geometry has a very central role in trying to understand homoclinic bifurcation and what happens after a homoclinic bifurcation. So let's discuss more in general this first statement I gave before quoting Poincaré, that homoclinic bifurcations are perhaps the main mechanism that create complicated dynamical systems from simple ones. And one of the reasons is that is related to this conjecture by Jacob that any, at least in dimension 2, homoclinic tangencies are typical among non-hyperbolic systems, in the sense that the union of uniformly hyperbolic systems with the systems which have some quadratic homoclinic tangency is dense in the set of diffeomorphism in any topology in dimension 2. In the C1 topology, it was proved in dimension 2 by Enrique and Martin. And in general, the general version of Palis conjecture also includes heteroclinic cycles. So if you take uniformly hyperbolic systems, systems which have homoclinic tangencies, the systems which have heteroclinic cycles, this union is dense among the diffeomorphisms. And Sylvain and Enrique proved, almost proved this in the C1 topology. So they replaced uniformly hyperbolic systems by essentially hyperbolic systems, which are systems with a finite number of attractors, which are hyperbolic and perhaps have some invariant sets which are non-uniformly hyperbolic. So perhaps some kind of non-uniformly hyperbolic Hochschuh, but sets of zero Lebesgue measure and most of the dynamics. So the attractors are hyperbolic and attract an open dense set with full Lebesgue measure. So most of the dynamics is hyperbolic. So I believe that Sylvain will talk about this tomorrow. So on the other hand, so homoclinic tangencies are quite common among non-stable, non-hyperbolic systems. On the other hand, homoclinic tangents create complicated dynamics. As I mentioned before, you have these works by Sheldon Newhouse, which show that after any homoclinic bifurcation, near any homoclinic tangency, you have open sets of diffeomorphisms presenting persistent homoclinic tangencies, and this creates complicated dynamical phenomena like infinitely many things for residual sets. Also, this famous work by Leonardo Mora and Marcelo Viana, who showed that after any homoclinic bifurcation under a dissipativity hypothesis, you may find strange attractors, so Henon-like attractors for a set of positive measure in the parameter space. And so these are two examples of complicated dynamical phenomena created in some sense by homoclinic bifurcations, by homoclinic tangencies. Even if you start with a Morse-Mail system, you create a homoclinic tangency. After the tangency, you may find all these complicated phenomena for some values of the parameter. So let's talk about some ingredients that we need to understand homoclinic bifurcations. And I will describe quickly because most of you are very well acquainted with this definition. So regular Cantor sets are one-dimensional hyperbolic sets. And they have some kind of self-similarity. So arbitrarily small parts of regular Cantor sets are diffeomorphic to big parts of them with uniformly bounded distortion if you are in the C2 topology, for instance. And so the usual ternary Cantor set is a regular Cantor set. It's maximally invariant by this expanding map defined in this union of two intervals. And a key question by Jacob is to decide when the arithmetic difference of two Cantor sets has non-empty interior. And I would describe this question much more precisely. So this became very important in the study of homoclinic bifurcations, but also in some problems in Diophantine approximation that I will mention very briefly in a while. So, of course, regular Cantor sets are fractal sets, and there are small fractal sets and large fractal sets, and most natural way of estimating the size of measuring fractal sets is to consider fractal dimensions. The most important of them is house of dimension. But in some sense, Newhouse introduced another kind of fractal invariant of fractal dimension, which is the thickness, which had a very important role in this story. But so this is a one-line definition of house of dimension. Of course, most of you are also used to notion of house dimension. I will not take much time on this, but this is a natural tool of comparing size of fractal sets. So regular Cantor sets are very important here because horseshoes in dimension 2 are locally diffeomorphic to the Cartesian product of two regular Cantor sets. So understanding well the geometry of regular Cantor sets helps a lot in understanding the geometry of horseshoes, and this is very important to understand what happens after a bifurcation. So the Hausdorff dimension of the horseshoe is the sum of the Hausdorff dimension of its stable and unstable Cantor sets, which are kinds of projections or quotients of the horseshoe by the stable and unstable lamination in some sense. So now we'll state, so perhaps the first central theorem in this theory relating fractal dimensions and homoclinic bifurcations by Jacob and Floris-Takens. Before that, there was analogous results by Jacob and Sheldon Newhouse on homoclinic bifurcations associated bifurcations of Mox's-Mayo map. So we start with a Mox's-Mayo diffeomorphism and you create a first homoclinic tangency, then you unfold it. And so Jacob and Sheldon proved that you have prevalence of hyperbolicity after the bifurcation. But Jacob and Floris-Takens extended this for homoclinic bifurcation associated to non-trivial hyperbolic sets, but with a geometric hypothesis. So if we start with a small hyperbolic set, for instance, with a horseshoe with Hausdorff dimension smaller than 1, and then you have a homoclinic explosion associated to this horseshoe, exactly like in this picture. You create a first homoclinic tangent and then you unfold it. You want to understand what happens for most small values of the parameter. Well, in this situation, Palis and Takens tell us that for most small positive values of the parameter, the system is still uniformly hyperbolic. So structurally stable, etc. So you have uniform hyperbolicity for most small positive values of the parameter in this sense. So in the sense that 0 is a Lebesgue density point, a full density point of hyperbolicity. Okay. So one of the so this situation is related to is very so it's deeply related with this problem that Enrique mentioned of considered intersections of pairs of regular Cantor sets in the real line. And the first approximation of this problem, so let's explain this picture. Again, let's go back to this picture. Sorry. Here. Okay. So when you have a homoclinic tangency, you may extend the foliations to neighborhoods, and you have a foliation that looks like a Cartesian product of an interval by a Cantor set. When you extend to an open set, you have a lot of kind of parallel lines. And the other foliation have a quadratic tangency, so have like a parabola. And when we extend this to a neighborhood, we have a lot of parallel parabolas. And so we have a lot of parallel lines, a lot of parallel parabolas, or some small C2 perturbation of this. You always have what's called a line of tangency, so a line where these two foliations are tangent in the sense that so the parabola here is tangent to this horizontal line. But we are really interested not in the extended foliation, but in the lamination, so in the stable and unstable laminations of the horseshoe. And they look like products of intervals or parabolas by regular Cantor sets, by the stable and unstable Cantor sets. And we can consider the intersection of these Cantor sets with this line of tangencies, which is this line here. And so we have a pair of Cantor sets. For negative values of the parameter, they have empty intersection. They are far away one from each other. For m equal to 0, you have a first intersection of the endpoints of these Cantor sets. And then for positive values of the parameter, they move like this. So you can create a lot of new intersections between these Cantor sets. And when you have a new intersection of these Cantor sets, you have a new homoclinic tangency between a stable and unstable leaf of the horseshoe. And new homoclinic tangencies are an obstruction for hyperbolicity. So this prevents the systems to be hyperbolic. If they want, after the bifurcation systems which are uniformly hyperbolic, they need to avoid intersection of these Cantor sets. A good first approximation of the situation is if you have a fixed Cantor set here, and the other Cantor set is moving with constant speed in the parameter space. So you have a family of one parameter family of Cantor sets. This is, say, K, and this is K prime plus T. And T is a parameter that moves the Cantor set. The set of values of T for which they intersect is precisely the arithmetic difference between these two Cantor sets. And so this Palis-Takens theorem is deeply related with the study of arithmetic differences of regular Cantor sets. As I mentioned, is the set of parameters T such that K intersects K prime plus T. So that the intersection is non-empty. This set is exactly the arithmetic difference K1 minus K2 here, K minus K prime, is the set of all difference X minus Y, where X is in this Cantor set and Y is in the other Cantor set. And what happens is that if the sum of the Hausdorff dimension is smaller than 1, then this arithmetic difference has 0 Lebesgue measure. Indeed, it has Hausdorff dimension smaller than 1. So for most translations, the Cantor sets have empty interiors, so you don't have new tangencies for this approximation. And indeed, Jacob and Flores could prove that in the real-life situations, or the Cantor sets are not translated, and well, you could have other new tangencies which do not correspond really to intersection of these Cantor sets, but anyhow they prove that if the Cantor sets are far away enough, so you have an estimate of the angle between the foliations, then they can prove that the system is uniformly hyperbolic indeed for most parameters after bifurcation. But this is a geometric tool that they use in order to start the proof of the theorem. So on the other hand, this statement on arithmetic difference is not true always. For instance, if the sum of the dimensions of two Cantor sets is larger than 1, then typical arithmetic difference for almost every lambda, K1 minus lambda K2 has positive Lebesgue measure. So in some sense, typically the arithmetic difference has positive Lebesgue measure. And Jacob became aware of this theorem at that time when he was working with Floris-Takens, and he realized that this hypothesis on the Hausdorff dimension of the horseshoe was really essential for this theorem, and that the situation should be dramatically different if you start with a large horseshoe. The horseshoe is Hausdorff dimension larger than 1. And this led Jacob to make this conjecture on arithmetic difference of regular Cantor sets, which was the main geometrical tool in his theorem with Floris-Takens. Because, on the other hand, Neuhaus already had these examples of persistent homoclinic tangencies. If you start with a very fat horseshoe, a horseshoe with thickness larger than 1, then the arithmetic difference of the two Cantor sets would be an interval. So you have homoclinic tangencies for any small value of the parameter after the bifurcation. But this hypothesis of Neuhaus, of course, implies that the sum of the dimensions is larger than 1, but is far from being equivalent to this. So you have a large open set of pairs of Cantor sets where you have Hausdorff dimension larger than 1, but a small thickness, so you cannot apply Neuhaus theorem. But anyhow, Jacob conjectured that typically if the sum of the Hausdorff dimension is larger than 1, then the arithmetic difference would have non-empty interior. And this should correspond in the situation of homoclinic bifurcations to two persistent tangencies for a set of positive density in the parameter. And, well, of course, this conjecture of containing intervals in the arithmetic difference was also motivated by this work by Newhouse. So this tau is thickness. So if the product of the thickness of two regular Cantor sets is larger than 1, then their arithmetic difference has non-empty interior. Indeed, will be a finite union of intervals. Okay, so I already described Newhouse results. And Jacob also became aware that Marshall-Hall in 1947, so much before Newhouse, already had some interesting and non-trivial results on arithmetic difference or sums, essentially the same, of Cantor sets in a very different context. He was interested in number theory, and particularly in Diophantine approximations. And he proved that if you consider the set of real numbers, say in the interval 0, 1, in which continued fraction representation, all the coefficients are bounded by 4, so you can only have 1, 2, 3, or 4 as coefficients. So this is a regular Cantor set in the interval 0, 1. And the arithmetic sum of this Cantor set with itself, so the set of all sums x plus y, where x and y are in C4, is a whole interval. It's the interval between square root of 2 minus 1 and 4 times square root of 2 minus 1. Indeed, in the Newhouse terminology, he proved that C4 has thickness larger than 1. So this is also a consequence of Newhouse theorem, but came before. And Jacob told me, and I was also interested in continued fractions and Diophantine approximations, then I also worked on this subject. This implies that the classical Lagrange spectrum, and also the classical Markov spectrum, contain a whole half-line, for instance, 6 infinity. This is not the largest half-line contained in this spectrum. Markov and Lagrange spectra are classical objects in Diophantine approximations. I think I will define them in the next slide, but just. So the regular Cantor sets appear naturally in this context because. So, what is the Lagrange spectrum? Lagrange spectrum is the set of best constants in the classical problem of Diophantine approximation. So you have an irrational number alpha. You look to good approximations by rational numbers P over Q. You have infinitely many approximations which error smaller than 1 over square root of 5 times Q squared. But square root of 5 is the largest constant which works for all irrational numbers. On the other hand, given an irrational number, you can try to find the best possible constant, which is given by this expression. It's the supremum of K such that this inequality has infinitely many rational solutions. This is at least square root of 5. For the golden mean, it's exactly square root of 5. And the set of the image of this function, so the set of the values of K of alpha, which are finite, K of alpha can be infinite. The set of finite values of K of alpha is the Lagrange spectrum. It begins discrete, so the first element is square root of 5, then you have 2 square root of 2, square root of 221 over 5, etc. Have a sequence converging to 3. But Marshall-Hall's theorem implies that at the end, it's a continuous set. So it contains a whole half-line starting before 6, but indeed in 4.52 or something. Okay, so, and this was very inspiring to me because I became very interested in this subject. I have some other results on the fractal structure of some parts of Lagrange and Markov spectrum, but I have no time to talk about this. Anyhow, so there was this conjecture by Jacob. Jacob and Jean-Christophe made some progress in this situation, both in the problem on regular Cantor sets and also on homoclinic bifurcations. For instance, they showed, this is a paper in Acta Mathematica, where they showed that if you have a homoclinic bifurcation associated to a horseshoe with dimension larger than 1, then if you consider 2-parameter families, so one parameter families of 1-parameter bifurcations, for most values of the second, for almost all values of the second parameter, you have positive density of hyperbolicity after the bifurcation. So it's also, in some sense analogous to Marstrand's theorem. So for you add an extra parameter, and for most values of the extra parameter, the arithmetic difference has positive Lebesgue measure, and this corresponds to positive density of a hyperbolicity in terms of homoclinic bifurcations. But it's much more difficult than Marstrand's theorem. And Marstrand's theorem was a kind of geometric inspiration for this result. They also considered the problem for Cantor sets, and they proved that if the sum of two Cantor sets, the dimensions of two regular Cantor sets is larger than one, you can perturb one of the Cantor sets by a conjugation, so by applying a diffeomorphism, a infinity diffeomorphism arbitrarily close to the identity, in such a way that the arithmetic difference has non-empty interior. So Marstrand's theorem was essential in both of these results. And, well, my thesis problem was to think about this conjecture by Jacob. And I did some progress in my thesis, and we solved it finally in my postdoc with Jean-Christophe. Jean-Christophe, as all of we know, was a great mathematician and a great friend of Jacob, of myself, of many Brazilian mathematicians, and a great friend of Brazil in general, of Brazilian mathematics. He contributed a lot, so he left us too early. But I had the privilege of working with Jean-Christophe in my postdoc, and we solved, in some sense, a strong version of Jacob's conjecture, of this conjecture. We showed that typically, if the sum of the Hausdorff dimensions of two regular Cantor sets is larger than one, then typically their arithmetic difference has persistently non-empty interior. So to be more precise, I introduced in my thesis this notion of stable intersection. Stable intersection is just a persistent intersection of regular Cantor sets that you cannot destroy, not only by performing small translations or applying small diffeomorphisms close to the identity, but also by changing a little bit the dynamics. And so it's an intersection that you cannot destroy by performing any kind of small perturbations in the Cantor sets. Depends on the topology, of course, you choose. But so we proved this theorem that if you consider the space of pairs of Cantor sets such that the sum of their Hausdorff dimension is larger than one, then typically most positions of intersections are positions of stable intersections. In particular, they have translations which have stable intersections. So the arithmetic difference has non-empty interior, but indeed the arithmetic difference will have dense interior in the sense that it's the closure of its interior. And the boundary has zero Lebesgue measure. So most points of intersections are points of stable intersection. Can give more information that indeed this open-ended set is a very large set, also in terms of measuring. So in the sense that if you consider parameterized families with a finite number of parameters whose image is contained in omega, then indeed the image will be contained in U for a generic set of such families. And also, you can not only have stable intersection, but these stable intersections. So in order to have the intersection to have positive Hausdorff dimension in a persistent way. So these are the main techniques of the proof. I don't have time to talk in detail on this. We have a recurrent compact set criterion for stable intersections, then a scale recurrence lemma, which gives a compact recurrent set at the level of scales. And then a key idea is to use this Herder's idea of the probabilistic method. So we don't create explicit perturbation, but we consider a family of perturbations with a large number of parameters, and we prove that for most parameters, you have a recurrent compact set, so you have the condition you need to guarantee stable intersection. So this also has a consequence on homoclinic bifurcations. We prove that typically after a homoclinic bifurcation associated to a large horseshoe with Hausdorff dimension larger than 1, you have positive lower density of persistent tangents in a persistent way. This is not full density always. You can have still positive density of hyperbolicity even in the case of dimension larger than 1. And the union of persistent tangencies and hyperbolicity typically will have full Lebesgue density. So, okay. So in higher dimensions, Jacob and Marcello extended Neuhaus theorem. So under a hypothesis of sectional dissipativity, they prove analogous result of Neuhaus theorem in arbitrary dimensions. So they find open sets of persistent homoclinic tangencies where residually you have infinitely many sinks. After a generic unfolding of such tangencies, you have, so if you look in the parameter space, so after a typical homoclinic bifurcation in the parameter space, you can find these open sets of parameters accumulating the first bifurcation parameter. So in each of these small open intervals, we will have infinitely many sinks residually. So in collaboration with Jacob and Marcello, we also stated and sketched that proof of a corresponding result to Palis-Takens and Moreira-Jacob's theorem in arbitrary dimensions for first homoclinic bifurcations. Homoclinic bifurcations, so the same situation, you have hyperbolicity for negative values of parameter, first tangency, and then the fact that you have a first tangency implies that the weakest eigenvalues are real, and this is important in the proof. So we have a kind of dichotomy in dimensions smaller than 1. You have prevalence of hyperbolicity. Dimension larger than 1, you have open sets of tangents with positive density at equal to 0. See, so this is published in Contrandi, a sketch of the proof of this. But the full proof has a lot of technical difficulties, so we have more people working with us in order to conclude this work. So we have Jamerson Bezerra, also Samuel Barbosa, Feitosa. So we are trying to finally, after 20 years, complete the proof of this theorem. But this is going very well, so we'll try to finish it soon. Okay, so I have other results related to this kind of techniques. For instance, for complex Cantor sets, we have recent works with Hugo Araújo and Alex Amudio, who are here. Have the thesis of Zulu, Wellstone Silva, on construction of blenders associated to horseshoes with large stable dimensions. Also with Jorge Eric, we studied the situation of projections of, or differentiable images of Cartesian products of regular Cantor sets. Okay, and then, of course, this monumental work by Jacob and Jean-Christophe, which Enrique described much better than I will do. Just have also some pictures. They have a hypothesis, so there's not, so you have a horseshoe, you have a generalized homoclinic tangent, so it's not associated to a single periodic point, but to a pair of periodic orbits. You have, but in the same horseshoe, you have this first homoclinic tangency, and then you want to understand what happens after the bifurcations. They have this condition on house of dimensions that Enrique stated that sum of the house dimensions smaller than 3/2. It's exactly this when the dimensions are equal. I think that in general you need this slightly more complicated, but it's a condition which goes well inside the region where the dimension is larger than 1, so you can have persistent homoclinic tangencies. And so they prove that for most parameters, so far with full Lebesgue density, as in Palis-Taken's statement, you cannot expect, as Enrique said, uniform hyperbolicity, particularly because of these theorems I mentioned with Jean-Christophe, but you have full density of non-uniformly hyperbolic Hochschuss, as Enrique described before. Of course, they don't think that this is the final condition, so it's another reason for studying this paper and doing this seminar, because they expected that this result could be improved. In particular, they expect that you can perhaps remove the hypothesis on house of dimension, but this will need a lot of work, because there are geometric, in some sense, algebraic geometric problems related with larger dimension. You need to consider high-order tangencies, which creates complication. But of course, the hope is that this would be true in general, and also that the techniques of this work should help to understand what happens typically in the standard family, so for a family of standard maps, which is a family of conservative maps. And of course, there's a classical and very important open problem, for instance, to show that typically these maps are non-uniformly hyperbolic, so have positive Lyapunov exponents. But they expected that their techniques should give light also to this very, very important open problem in dynamics. So thank you very much. So this is a picture of Jacob and Jacques-Christophe in San Marino. I have a lot of references, so thank you very much. Parabéns, Jacob. Ficou muito ruim, né? Cara,